let's start just by a brief recap of what we did in the third lecture. So what we did is that we started from the replica symmetric solution, and then we computed its stability. And so we had a phase diagram like this one. So again, here we have sigma, and here we have the fraction of constraints. So this is the replica symmetric. So this is the replica symmetric SAT unsat threshold. So here the problem is unsat, and here it is sat. This is the convex regime. And this is the non-convex regime. And what we've shown is that here there is a line. So we did this computation at the replica symmetric level. And what we have shown is that here replica symmetry is always okay. It's always stable. So the replica symmetric solution is always stable. Instead, here there is a line that separates two phases. So here the solution is replica symmetric in the sense that the replica symmetric ansatz is stable, and instead here replica symmetry is unstable. Okay, so when you are in the non-convex region, the SAT-unsat transition lies inside a part of the phase diagram where the replica symmetric solution is wrong. And so in order to compute it, we need to do better than the replica symmetric solution. So this reflects the fact that when you are in the convex region, as we discussed, you expect that the space of solution is convex. And so you have just one region that shrinks to one point when you cross the SAT-unsat transition. Instead here, since you are in a non-convex regime, the space of solution is clustered. Okay, you can expect that it's clustered, and this is what the stability computation tells us. And so you have islands of solutions, and they just shrink to zero, shrink to one point when you cross the SAT-unsat transition. Okay. So starting from this, we introduced a replica symmetry breaking scheme. And in particular, we discussed Parisi's hierarchical ansatz. And we have shown that it has a deep physical meaning, in the sense that it describes a space of solutions where the solutions are organized into clusters. So, for example, we have computed the P of Q, the probability distribution of the overlap, and we have seen, for example, that at the 1 RSB level, this is 1 minus m. Yes. So this is the 1 RSB computation for P of Q, and this was telling us that so the space of solution is a big cluster And inside of this cluster, you have subclusters. And if you take two typical solutions inside the inner clusters, they have a typical overlap that is Q1. While if you take two solutions that are in different clusters, then their typical overlap is Q0. Okay. And of course, we can generalize this to a full replica symmetry breaking scheme where replica symmetry breaking is broken at all levels. And so you will have a full hierarchy of clusters into clusters and so on. Okay. Okay. So the plan for this lecture would be the following. So what we would like to do now is to try to implement this scheme to compute the properties of the Sat-on-Sat transition. Okay. And so the plan of this lecture will be the following. So first of all, we will start again from the S of Q that enters in the computation of the free energy, and we will try to compute it at the full RSB level. Okay, so we will plug inside this expression a hierarchical ansatz for Q. And then, of course, once we have it, we need to take the saddle point equations with respect to Q. And so we will describe the saddle point equations. And then I would like to describe some consequences of these saddle point equations, and in particular, marginal stability. And then finally, I don't know if I will have time, but maybe it will be the next lecture. And finally, I would like to describe the critical properties of the jamming transition, or Sat-on-Sat transition, of course. Okay. So let's start again from the S of Q. So again, this is 1/2. So this is the expression that we obtained in the last lecture. Okay, so I will do the computation in the Sat phase. So I will assume that e to the minus beta v of h goes to theta of h. Okay, so this is Sat. And what I will do is to compute separately this term and this term, as we did for the stability. Okay, so let's compute 1 and 2. Okay, so I will not do the details of the computation of this term because it is quite standard in the sense that there are already, I mean, okay, it's not very deep, so it's just technical, and I will give you the reference to compute it. So the log, so let me do the following. So we have a matrix QAB, and we are parameterizing it with 1 that is the diagonal part. And then we have Q of x. Okay. Okay, so this Q of x is the function that parameterizes the okay, let me just make a brief recap of this. So we introduced the replica symmetry breaking scheme, and so we have a Q that is a matrix that is 1 on the diagonal, and then here it's block diagonal, and this is, for example, a 1RSB structure where here we have Q1 and Q0, and this is M0, and then we can iterate this construction by breaking further the innermost blocks. And when we take the n to 0 limit, we can represent this construction by a function, Q. This is n, this is 1, and this is a stepwise function. Okay, so this is M0. This is Q0, Q1, up to Qk, if this is a KRSB construction. This is 1, and so on. Okay? And then when we take the k to infinity limit, then we can think that this converges to a smooth function, okay, that we call Q of x. Okay? Okay, so the log of the determinant of this matrix, okay, that is obtained with this limit, so we take the KRSB ansatz and then we take the k to infinity limit, so this thing can be computed exactly, and I'll give you the expression. So I will not derive it just because it's, yes?
I didn't understand from last time, why do you take a continuous function in between M0 and K?
No, it's, no, there is nothing deep here, in the sense that, I mean, in principle, this can be whatever function you want. Yes. It has to be an increasing function, at least. Yes. So it can be flat or at least increasing. And in general, from the general solution, you always have two plateaus. But for example, this is, I mean, it's generic, but it's not universal. For example, if you take the SK model, so the Sherrington-Kirkpatrick model, it's a spin glass, then you have that this plateau is not there in zero field. And so you have just something like that. But typically, you have two plateaus. Okay.
The plateaus result, I mean, you will obtain them.
Yes, you will obtain them from the solution of the saddle point equations. It's not something that you have to put by hand.
Okay.
Okay, it comes from the solution of the equations. Okay. So I just show this because it's a kind of generic picture, but there is nothing that, okay? Okay. Okay, so okay, let's compute 1. So this is 1/2 log that of Q. So this can be computed exactly. I will not do the details because they are not so deep, it's just technicalities. But they can be found in this paper. So it's Mesar, Parisi. So it's an appendix. It's the appendix of this paper, so it's replica field theory. For random manifolds. And it's a J phys I 1. Okay, so the formula for this is the following. So maybe I will try to derive it in the notes, but I don't want to discuss it here. So is this one. So and I will tell you all these things. Where this thing, the average of q, this is just the integral from 0 to 1 of q of x. And this function, it's just x q of x minus the integral from 0 to x, the y q of y. Okay, so this is a formula. If you have the profile q of x, then you can compute it, compute the log of the determinant with this. So it's not
q varies more or less from 0 to
1. Yes. Yes. So it's I've taken the n to 0 limit. So here this goes to 0, and this is a function from 0 to 1. Okay. Okay, so this is
that formula is absolutely general. It doesn't depend on anything of your concrete model.
no. I mean, it's if you have an ultrametric matrix of this kind.
General, yeah.
Yes,
Just
it's very
Q
general.
will depend on your concrete.
Yes, yes. So and I mean, here I've assumed that on the diagonal there is 1.
Yeah.
But if it is not 1, what you have here, all these ones that appear here are let's say q diagonal. Okay. So if you have something on the diagonal, this will be qd, this will be qd, and this will be qd. Both. But okay, so here we have 1 just because we have a spherical model. Okay.
But sorry, is q of x continuous if x goes to 1? Does it have to go to qd?
Sorry? No, it doesn't have to go to qd. Actually, it has a physical meaning. This thing should not be 1. It will be 1 when we cross the Sat-Sat transition. So it should not go to 1.
And in this formula, it's not 1?
No.
Okay.
QD can be generic, and the Q maximum, the maximum of Q of x should be less than QD.
Less or equal.
Less or equal, yes. And when it goes to QD, I mean, we will see that it's the Sat-Sat transition. Okay.
And it's just experience from you who work on this problem that this Q is more or less continuation. His question is somehow still continuous, you know, because maybe it goes till something till 1/2 and sort of jump to.
It can. I mean, I will show you that this is. I mean, in some region of the phase diagram, you can have this. So you can have discontinuities, but then I mean, I will underline that when you go close to the Sat-Sat transition point, there is always a continuous part close to the maximum, close to here, and this will be very. I mean, this is crucial. Okay, thanks. Okay, so maybe in the notes I will try to make the derivation of this, but you can also find it here. And now let me.
This journal died.
Sorry?
This journal died.
What?
This journal is dead.
Is that? No, but you can find, there is the archive hole that contains the PDF of this. So I think that it can be downloaded, at least from the institute. Okay. So instead what I would like to do is to perform the computation of this term, which is something that is less trivial than this one is already non-trivial, but the other one is more difficult, and there are nice equations coming out from it. So I would like to do it. Okay, so 2 is alpha log. Okay, so the way I will compute this term actually is contained in a paper by Duplantier. And the title is Comment on Paris' equation. For the SK model. Glasses, and it's a JPC 1428. And the same line of reasoning can be found in Nishimori's book. So, in order to perform it, let me introduce the parameterization. So, here I have to be precise. So, I start from a KRSD parameterization, and then I will take the limit where k goes to infinity. So here I have n, and I will call this n minus 1. So this is just notation. I will call n minus 1. 1 will be m k. And then here I have n0, n k minus 1. Here I have q0, q1, qk. And in particular, q minus 1 will be 0. Just notation. Okay. And now we introduce some matrices. So let me introduce this matrix, 1 hat I. So this is a matrix that is like this. So it's a block diagonal matrix. Outside there is 0, and inside these diagonal blocks, the elements are all equal to 1. Okay. And the size of these blocks is m I minus 1. Okay. Okay, so with this, you can write Q, the matrix Q, as sum from 0 to k plus 1, Q I minus Q I minus 1. Okay. So maybe yes. So actually, okay. So you see that. Maybe I'll run this. So for I equal to 0, 1, 0 is this with mi minus 1. Okay, there is wait, no, it's okay. So maybe I can do the 1RSP. So if you want to, so let me consider the RS case. Okay. So here we have just two terms. So we have, so k is actually 0, right? Because it's the RS case. So this is from 0 to 1. And then we have, okay, I have to introduce the notation. So we have Q1 minus Q. Maybe that's it.
It's up to k, not k plus 1.
No, wait.
Because there is no q1.
So maybe it's Q. Yeah, exactly. So here in this case we have, so in Ellis case, we have just a matrix that is like this, right? So it's 1 on the diagonal and it's a Q0, right? So we say that Qk plus 1 is equal to 1, just by notation. So in this case, this is so in principle, this is Q0 minus Q minus 1, but Q minus 1, we say that this is 0. And then here we have 1, 0, but 0 is n, right? Because it's a matrix of sides m minus 1, and m minus 1 is n. So this is a matrix of sides n times n and full of 1. Okay, plus, and then we have 1. So we have Q1, but Q1 is 1, minus Q0. And then we have a matrix of sides Q1. And this one is just the identity, right? Is it okay? So the notation is okay. Do you agree? Okay, so then we can reconstruct the one as the answers the same way. So let's keep it. And now let's plug this inside the expression of the term. So we have, so let's consider the differential operator. So we have 1R. And this is 1R. Okay, so just I plug this inside that expression. Okay, and therefore we have E. And here we have probably. Okay, so now what we do is that we look at this thing and we start from the innermost block. So So the innermost block is realized when I take I that is equal to k plus 1. So I'm just starting from the innermost block of this matrix. Okay. And I isolate this innermost block. Okay. So I write it here. So this will be E. I forgot here the sum over ln, right? So this is sum. Okay. And then I add the innermost block. So when I take k plus 1, here this is 1, because it's the diagonal part. And so I have 1 minus 2k, right? And then I have this matrix becomes just the diagonal matrix. So I have the sum over L, the L squared. And then I have product okay, so I just isolated the innermost block. And then now I can apply this differential operator to this. And this we know how to do. So it's E 0, 3. And here I have the product of S from 1 to n, and then here I have just the Gaussian convolution with this function. Right? So this is what we used to get the replica symmetric result. Okay. Now we call this function, as I did the last time, g of 1 and h, hs. And the meaning of this one now will be here. I will tell you. So you see that this is, so here what I'm putting is the level at which I did this operation. So in particular, this one here just refers to the innermost block. Okay. Now, I mean, as soon as we go on with the computation, it will be clear what this one is.
Pierfrancesco,
Yes.
can you recall the definition of gamma?
Gamma is just the Gaussian convolution with variance 1 minus q.
Okay.
The function. So
Okay.
I will write it to record it. Sorry. So gamma A star of H. This is okay. So it's just a convolution between a Gaussian and the function that is here. Okay. So from here you see that qk cannot be greater than 1, otherwise this, of course, it has no meaning. It can go to 1, and we will see that this is the case. But it cannot be greater than 1. Okay. So now we go on with the iteration. So we take the innermost block of this differential operator, and then we apply it to this function. Okay. So what is this? So I write it here. So we have here we will have k minus 1 somewhere, I don't know. And then we have, so this is one thing. And then I have to call. I will not write that this must be computed at h that is equal to minus sigma. Okay. So now we have this, and we can compute it. Okay, where do I write it? Okay. So you see that this is a matrix. This block diagonal, okay, and the diagonal blocks have just dimension m k minus 1, right? Okay, because it's 1k. So you see that this thing can be written this way. So when I compute this product, so we have this differential operator, these differentials, they just act on diagonal blocks, right? Do you see? And so I can just write this product as a product over the blocks, the diagonal blocks, okay. And then I have the product inside the blocks. Of theta of h. Okay? And so when you since at the end we want to compute the derivatives in a point where all the h are equal, okay, this is just equivalent to, okay, I will write it and then we'll discuss it. So there is this term here, and then this is just the product, okay, from S from 1 to n divided by m k minus 1. So you see, this is the number of blocks, okay, n over m k minus 1, right? And then what do I have? I have just the Gaussian convolution. And now this thing, since we want to compute everything on the same h, will be this function. So actually this is a gamma of 1 minus 2k. So let me write it properly. So it's just this times this to the power m k minus 1. So it will be g of 1 h. Now this h has an index s, but this is a block index. And here there is m k minus 1. Okay? So you see that, okay, let me call this one, of course, is by definition equal to mk, okay, because of the parameterization. And now we'll call this function, okay, let me write it here. This function, I will call it g m k minus 1 and h, okay. So you see that this index is just telling you at which level of the iteration you are. And now we can go on with this, with the construction, okay? So once we have at the, let's say, at a given level, so at a given level, the computation is similar to this one. You see that it reproduces, right? So you have just a function here and a product over the blocks, and then you have a differential operator. So once you go on, the generic term that you see that appears is the following. So iterating this procedure, so what you have is the following. So you have so after time t, so after let's say t plus 1 iterations, so you have t I minus t I minus 1. Then here you have the clone. Okay. So this is the generic term that you have the iteration t. Okay. And here we have defined, so we have defined g for a generic index I. Okay, so this is the generic step that you take, right? Is it clear or is it clear? Okay. So now what I would like to do is to take a continuum limit for this equation. Okay, so up to here everything is done in a discrete way. Okay, so you have k, so you have q that is a stepwise function. And now what I would like to do is to take the continuum limit in which this function becomes continuous. And so in this case, what you expect is that these two become close, right? And of course, the mi minus 1 and mi become very, very close. So what we will do, and of course this is not rigorous, but let me do it. So I will say that mi minus 1 is equal to mi minus dx, where this is smaller. Okay. And I will call mi x, so this is x minus dx. And qi minus 1, this is equal to q dot of x dx. Okay. Okay, now we start from this, we plug this, and then we develop at first order in dx, and then we will get a differential equation. Okay, I will do it. Yeah. So we have G okay. And now let me develop this at small dx. Okay, let me do this one. So this is just so I indicate with a dot a derivative with respect to x. And now let me consider this one. So I represent this with a differential operator again. So this is 1 So I just say that this Gaussian convolution is this differential operator. And then I have so of course this can be written as e to the 1 minus 2x of x out of g, which it is easy to. Okay, so let me develop this. So this is 1 plus and then here I have okay. And so this is G. And I have this term. And then I have this term. So it's minus 2x over x g. Okay. Now let's take these two together. So we write here. And so there. Okay, so these two go away. And so the resulting equation is just if you have a Q of X, then you can reconstruct this G by solving this equation. And of course, we have to give an initial condition for this. And remember that we had G of mk that was equal to 1. This was gamma of 1 minus qk. And now when I take the continuum limit, this becomes just, this is q of 1. Okay? So you have the initial condition, and this is the flow equation. So what you can do is that you can introduce a new function. Maybe, can I erase this part? So what you can do is that you can introduce a function f. This way. So you introduce f such that g is equal to this. Okay. And now you can, instead of writing an equation for g, you can write an equation, a flow equation for f. Okay, so the initial condition is easy. It's just the log of g.
Why you call it initial condition? Looks
Sorry?
more like, why you call it initial? It looks more like boundary condition.
Boundary condition, yes. Well, it's just because I interpret this, so I interpret x as a kind of time index. So I'm starting from 1 and going backward to 0.
No,
I agree with that.
it's a boundary. Yeah, just to light up a little bit.
Okay. Now we can plug this into this equation. So we have okay, so we have g dot. It's just equal to g. So I indicate the derivative with respect to h with a prime. Okay, so this is equal to g. And then if we plug this into this equation, then we get an equation for f. Which is and the initial conditions, so the boundary conditions log gamma 1 minus q1. Okay. Okay, so we transform this term in a kind of differential form. And now we can go back to the evaluation of the term that we wanted to evaluate. So let me write. So this equation was derived in the context of the SK by Python. And whenever you have this structure, this differential structure, so with this term.
You mean this or similar?
Sorry?
So exactly this equation?
Exactly this.
So up to now still everything is generic in some sense?
Yes, exactly. That's what I was saying. So whenever you have a term like this, and then here you have a product from 1 to n of some function, everything is generic, so that equation follows.
Assuming Q.
Sorry?
Assuming Q. I mean,
Of course, you have to assume that Q has this structure. So, but once you have assumed that the Q has this structure,
yeah.
and the diagonal term is 1, otherwise here you have QD. But apart from that, the equation is really the same.
Okay. Yes.
Okay, so we started from this. We got the equation. So look, this is a flow equation that starts from the boundary condition that is at x equal to 1. And now, of course, we would like to compute this. So we started from the innermost block, and then we want to go outside, up to the externalmost block. And so this term will be just so evaluated at h. Okay. So this is the result of this integration. So integrate this equation starting from this initial condition up to here, and then the term that enters in the S of Q is just given by this. Okay. Now we can take the n to 0 limit. And this is just so it's log. So here I use f. So I rewrite g in terms of f. This is m. Okay. Then I develop a small m. And the first term is 0 just because gamma of 1 convoluted with 1 is 1. So the log is 0. So we have just n alpha. Sorry, not the log. So here I have m0, but m0 is very close to n, so I can replace it with n, and n is going to 0. So I have just this. Okay. So in the end, and then I will stop for a break. So the S of Q is just 1/2. This is the term that we discussed before. So now the comment is the following. So of course this expression depends on the profile Q of x. Okay. So this depends on Q of x. But you see the dependence is quite difficult to handle in the sense that this term is explicit in Q of x. Okay, it explicitly depends on Q of x. But this term depends on Q of x through this function. Okay, so you have a profile Q of x. You have to plug it inside the flow equations. Okay, you solve the flow equations and then you get this term. Okay, and now the problem is how to take the variational equation with respect to Q of x. Okay, is it clear? Okay, let's make a break and then I will do the presentation. Right. Okay. Okay, so what we want to do is to let me write it here. So what we want to do is to take the subsequent equation. Okay. And the problem is how to do it. Okay, so there is a simple solution that is using Lagrange multipliers. So you want to enforce this equation. Okay, you just add two Lagrange multipliers, one for the flow equation and the other one for the boundary condition. So we start from this and then we add the, okay, let me, okay, I will write it here. Then we have two Lagrange multipliers. Okay, so we add them. So this prefactor is irrelevant, but I use it for to have better, let's say, to have later simpler equations. So I have a Lagrange multiplier for the initial condition. And then I have a Lagrange multiplier for the flow equation. Sorry?
Okay, so here.
P. These are two Lagrange multipliers. Of course,
It's not numbers, they're not numbers.
They are functions. Okay? Because you want to enforce this for all h and for all h and x. Okay, and now what we have to do is to do this variational problem, but now what, now also f is a variable, right? Because now f is free, and only at the end will be enforced by the flow equation. Okay. So, of course, if you take the derivatives with respect, the functional derivatives with respect to p1 and h and px and h, you just get back the flow equation for f and the initial condition, right? And now what I would like to do is to take the derivative with respect to f of 0 and h and x and h. Okay. So, if you take the derivative with respect to f of 0 and h and you put it equal to 0, then you get just the P of 0 and H is a Gaussian. That's good. Basically, you are just deriving this term. Okay. And then if you take what you get is this differential equation. Which is close to the equation for f, but it's different. Right. Okay, so this is a linear equation. Okay, you see that here it has a different sign. So there it was minus 1/2 q dot, here it's q dot half. But it's linear, it's a linear equation.
But you multiply p by f, so it's linear, but
Yeah.
it's inhomogeneous. It's
Yes, yes.
still horrible.
Yes, it's still. I agree with you. Actually, I mean, when you try to integrate numerically these equations, that one is kind of simple in the sense that you can go back to the KRSB representation. It's just a convolution of Gaussian integrals. Okay, you have a Gaussian integrals, then you have another Gaussian integral, and so on. Here, you can still write a convolution, but it's more involved. Okay, so the last thing that we have to do is to take now the variational equation with respect to Q of x. Okay, and so we will have the derivative of this term, and then we have Q of x appearing here. And let me do it. Okay, it was not smart. Where is this? So the derivative of this term here with respect to Q of x just gives you you can do it easily. So it gives you 1/2 Q0. So this is for x different from 0. And what you will see if you do the computation properly is that the equation for x different from 0 reduces to the case x equal to 0 when you take the x to 0 limit. Okay, but let's assume this. And here I'm introducing lambda. So lambda is 1 minus q minus q of x. This is also equal to 1 it's not very important. Okay, it's not very important. So it's this, it's the quantity that appears in the numerator of this. And then we have plus alpha. So dy. and then we have f dot plus q dot. So now we have to take this functional derivative. Okay, so let me just focus on this. Okay, so what you can do is that you can make the integral by parts. Okay. And then when you take the functional derivative, this just reduces to, you have a minus sign that comes from the integration by part. And then you have the integral of h is a 1 over 2. Okay. Now we do the derivatives, and what we do is that we use the flow equations. Okay, so let me rewrite them here because I increased them. So we have f dot is equal to minus q dot over 2. And p dot so let me use it. So this is minus 1/2. So you see that you have a term where this derivative acts on this, and then you have a term where this acts on this term. So the term where you have p dot, you have this. And now what we can do is that we can make integration by parts over h. And so this becomes so making integration by parts, you get just p. Then you have q dot over 2. And then here you have plus, because here you have to make two integration by parts. Here you have just one. Okay, and this acts on this. Then you have plus right? Just to use the integration by parts applied to this flow equation. I'm assuming that all the boundary terms go to 0. Okay, and then this is the case because P is actually a Gaussian for H that is very large. Okay? So now we have just to take these derivatives. Okay, so this is equal to now we have q dot over 2. then we have this applied to this. And so we have f, the fourth derivative with respect to h of this, plus 2x prime f term plus 2x f7 squared, and this is this over this term, and then we have this over this, which gives plus 2x f prime f term, and this applied to that. And then we have this and this, which gives plus 2x prime, sorry, 2x squared for x squared f prime squared f7, right? Okay. And now we have to take this derivative applied to this term, and we will use again the flow equations for f. So this is the first term, and then we have plus okay, so I've just taken this derivative. Is it okay? Okay. And now we can use the flow equation for this term and this term. So we can take derivatives of the flow equation for f. So let me do it here. Okay, so we need the second derivative with respect to h and the first derivative. So we start from the flow equation. So we have okay? And now let me use these two, insert these two terms. So I will rewrite it here and then I will erase this term. So it's plus. So let me isolate this term. Okay. So we have plus f prime squared. And now these two terms are proportional to minus q dot over 2. So it's plus, so it's minus q dot over 2. And then we have the full derivative plus 2x f second squared plus 2x prime third. And this is this term. And then we have this term. So it's plus 2x f prime. Then we have this. So it's f third plus 2x prime f third. And that's what we should close this. Okay, so you see that this term and this term go away. This one, so we have this one, this one, this one, and this one. They go away. And then we have this term that goes away with this one. And this term that goes away with this, right?
Yep.
And so the end is, so we have minus 1/2. Okay. So if we take back that equation, we have, okay, I can write it here, or maybe directly. So this term reduces to so this equation just becomes, so the 1/2 can be eliminated. The sign -1 goes to the other side. So this is equal to
Isn't it alpha in front?
yes. Okay. Thank you. Okay. So we have two flow equations with two initial conditions and a closing equation that is this one. Okay. Now, a simple thing that we can do is to check that these two equations just give back the replica symmetric saddle point equation. So how to do this? So a replica symmetric solution is just given by a Q of x that is flat, right? And therefore Q dot is equal to 0 in this case. So for this, since Q dot is equal to 0, then they just don't evolve. Okay, they are fixed to the initial condition. And we know that the initial condition is now I can use Q1, but Q1 is just this Q. Okay, let me call this Q. Sorry for the abuse of Q. So this is Q. And P doesn't evolve, no? So it's gamma of Q. Okay? So if we plug this into this, so this term is not there because Q dot is 0, and then this term is low. It's Q divided by, so the average of Q is just the integral, so this is equal to Q, right? So we have 1 minus Q squared equal to alpha. So these are Gaussian, so it's 2 pi Q. And then we have the first derivative of this and this is the replica symmetric saddle point equation. Okay. Okay. So now what I would like to do is to do one thing that can be, for the moment, is unjustified. But what I would like to do is to take the derivatives with respect to x of this equation. So this equation is in general holds for all x from 0 to 1. And therefore I can take the derivative of the right hand side and left hand side. Why? I will tell you. So what I would like to do is to take the x of that equation, so it's 0. Let me write this way. It's not very. Okay, so the derivative of this is just, you can show that it's just q dot. And then you have this, so you have okay. Now you see that you have again this structure. So we had already before in order to derive this equation. So you take these derivatives and then you use the flow equation for P and F. Okay. So if we okay. So I mean, this operation is not is as difficult as the other one, so I will not do it. But you can show that the result of this, once you use the flow equations, is just alpha and then you have epsilon. Okay.
I'm not sure. How many derivatives do you
The
have?
first dx shouldn't be.
Too many in the middle. In the middle.
Ah, sorry. Sorry. Yes, yes, yes.
Just virtual. The first was virtual.
Okay, sorry. Yes. Okay, so if you take this derivative, then you get this. Again, you have to use those equations. And sorry, that is not one thing. You have this. So you have q dot over lambda squared equal to q dot times this function. Okay. Now, if q dot is different from 0, what I can do is that I can just erase this q dot with this q dot, and I get 1 over lambda squared equal to alpha p f dot squared. Okay? Now, let me compute this. I do something that I don't have to do. So I compute this equation on the replica symmetric solution. Okay. So this in principle I cannot do because Q dot for the replica symmetric solution is 0. Is different, is 0, sorry. Therefore I cannot use this equation. But let me compute it on the replica symmetric solution. Okay. So let me do it. So you see the relation.
Yes, that's it.
I raised the initial. Okay, so lambda of x. Now, so when you compute it on the replica symmetric solution, this is just 1 minus q. So this is q of x equal to, and therefore this is 1 over 1 minus q squared equal to alpha. Now, P is a Gaussian because it's equal to the initial condition, so it's and this is what? This is the second derivative with respect to h of log minus sigma. There is a minus sigma. Ah, no, let's put it here. So remember that the P0 of H is gamma of Q H plus sigma. So this is this. So see that this equation is exactly, so this equation is satisfied when you cross the D'Almeida-Tavares transition. So if you take back the computation that we did for the instability of the replica symmetric solution, so we have this phase diagram, right? And this is the instability line of the replica symmetric solution. So this equation is satisfied exactly on this line. You can take back the equation of the computation of the stability of the replica symmetric solution, and we had the Derivation eigenvalue was minus 1 over minus q proportional to, now I don't remember exactly, plus alpha, and then exactly the same expression. And then we had the second derivative with respect to h of log of this theta function that is exactly equal to this of h divided by square root of 2 to 1 minus q. So this becomes equal to 0 exactly, I mean, you see that this equal to 0 is exactly this equation. Okay. So the reason is the following. So suppose that you are in this region, okay? So here the solution of the full RSB equations, of these flow equations, is a Q of x. There is something like that. Okay. Now when you go from these points towards the replica symmetric solution, of course the evolution of this equation is such that this thing just goes to a line. Okay. And in this region, where Q of x is such that Q dot is different from 0, this equation holds. Right? Is it clear?
Can you repeat, please?
So this equation holds whenever Q dot is different from 0. Therefore, it holds for the x that are in this region. Okay. Okay, and this region is shrinking because these two plateaus just are going together in order to have a flat part, right? So exactly at this point, this equation still holds. And then when you cross this point, it doesn't hold anymore. Okay? Is it clear? Therefore, this equation just tells you where replica symmetry gets broken. Okay? So, the point is that we have computed this equation on X on a replica symmetric solution. But of course, this holds for a full set of X that are such that the Q of X is not flat. Okay. And therefore, this is a kind of this just comes out naturally from the Fourier SB structure. So whenever you have a Q of X that has a continuous part, then this equation holds. And this is called. So what you can show actually is that, okay, so this equation is connected to the stability of the Fourier SB solution. So as we did for the replica symmetric solution, we computed the stability, right? The stability of the replica symmetric assumption. Here you can do the same. You can compute the stability of the full replica symmetric gradient solution. And this was done by the Dominicis and co-workers. Actually, it was also done by Taules, we're exactly close to the transition line here. Okay. So then the full solution of the stability of the Fourier SB equations was completed by the Dominicis, and it showed that the Fourier SB solution is marginally stable, in the sense that you never have eigenvalues that become unstable. But you have a lot of eigenvalues of the stability operator that are equal to 0. And this is expressed actually by this equation. So this equation is telling you that the full replica symmetric solution is marginally stable. Okay. And you see it from the RS computation in the sense that it already gives you the instability of the replica eigenvalue at the replica symmetric gradient position. Okay, yes?
So when you talk about stability, is that in the saddle point? It's not the saddle, right?
Yes. So you do the saddle point, then you have to do what we did for the replica symmetric computation. We have to take the saddle point, develop S of Q around the saddle point, and compute the eigenvalues of the stability operator, so the quadratic form that emerges, right? So you can do it with these hierarchical ansatz, and what you can show is that if Q of X satisfies the set of equations that we obtain, then this quadratic form is at least marginally stable, in the sense that you have either the eigenvalues that are stable, or you have a set of eigenvalues that are equal to 0. And the set of eigenvalues that are equal to 0 are translated by this equation. Okay, so this equation is telling you that you have a set of eigenvalues that appear in the stability of this solution that are equal to 0. So the Fourier SB solution is marginally stable. It's said to be marginally stable.
Okay, but what I have trouble to see is that for me, like, we have the matrix at the beginning, which is n times n.
Mm-hmm.
So you have like n squared parameters
Yes.
in this matrix.
Yes.
So if you take Q of X is just continuous, you over-parameterize your matrix, so you cannot have all the matrix in this one. So if you are unstable.
No, of course, you have to do it when n goes to 0. So when n goes to 0, I mean, what happens is that this matrix becomes a function. So you have a functional, and then you have to develop this functional second order.
Okay, but then if it's Fourier SB and it's unstable, you still have solutions in the matrix Q that are not verified by this hierarchical concept.
No, what do you mean? So what I say is
It's
that
always stable
It's
or
always
marginally stable.
Oh, okay.
He never
Or
said
marginally-
that it's
Sorry.
unstable.
So,
okay.
yes.
Okay. So what I will okay. So this actually what you can show is that this equation that tells you that the Fourier solution is marginally stable is directly connected with the marginal stability of R-sphere Pockins. And I will come back to that when we will do the solution, the scaling solution of these equations close to the Saturn-Sat transition. Okay, so this thing has a kind of deep physical meaning. Okay. So the last thing that I would like to tell you is that you can play this game again. So you take this equation and you take again a derivative with respect to x. And the equation that you get, where do I write it? Okay, so so the equation that you get, if you take the derivative of this, is the following. So you have, so if Q dot again is different than 0, then you have x that is equal to lambda of x divided by 2. And you have okay. So again, this follows from just the flow equations for f and t. Okay. So, and it holds only for q dot that is different than 0. So when you, if you take this phase diagram here, so you see that this equation holds in this region for x that are inside this interval. So where q dot is different than 0. So when you go from this point towards the RSB transition line, this function is like that. Right? So, and therefore this equation is just telling you where you start to become non-flat. Okay, it's where the q of x breaks in some sense. Okay, and we will use it. So we will use this equation when we will describe the scaling solution close to Gen. So let me just conclude with the phase diagram. So using this set of equations, you can show that actually the phase diagram is a bit more complicated than this one. And it's like this. So here there is, okay, let me. So this is the replica symmetric Saturn-Sat transition, which in principle is wrong for sigma negative. So this is the instability of the replica symmetric solution. And then what you have at some point, you have other two lines. And here there is another line. Okay, so here the solution is replica symmetric. Here in this region, the solution is of the full RSB capital. And what happens is that when you reach this point, actually here, the solution is 1 RSB. Okay. So here, if you are in this region, the profile of Q of x is just like that. And when you reach this point, so here so this point is, we call it sigma RFOT for random first order transition. This is something that we said in the first lecture. Actually, it turns out that the space of solution here is organized really like in structural classes, in the sense that if you look to the Boltzmann measure, so remember that we had the partition function that is so we are in the beta to infinity limit because we are studying solutions. So what we can show is that this Boltzmann measure here is dominated by solutions that have a finite complexity, a finite configurational entry. So I don't know if I'm going too fast. Okay, so here you can plot the internal, so you have clusters. Each cluster has an internal entropy, and then you can plot the number of clusters, the log of the number of clusters with that internal entropy. And this is the complexity. And this is like that. Okay. And in this, at this point, you are dominated by clusters that have the highest, that are the most numerous. Okay. And then when you go in this direction, you are just dominated by clusters that become less numerous. And when you reach this line, the clusters that dominate the Gibbs measure are the ones that have zero complexity. And this is this transition line here. And when you cross it, you are frozen here. And then at some point, there is a transition here that is called Gardner transition, where actually, if you look to the Q of x, so you see that here you have a structure like this one. So when you cross this line, inside these states, there is a hierarchical structure appearing. So each one just become cluster, okay? And this corresponds to have here a solution Q of x that is like that. Okay, so you will have a continuous part here. And this line is always like that, okay? So you always have a Gardner transition before. So in this region, the solution is always of the polarized. And this line is always in a region where the Q of x has a continuous part. Okay?
And so this line, top line, you essentially should erase because it's
This one is
because it's
the way in which we
fictions,
computed is replica symmetric, but there will be a line computed with this that will be in this region. Okay. So technically what you can say is that these lines have always this plateau here that is less than 1. So they are always in the SAT phase. Because the SAT-answer transition is characterized by the point where this plateau goes to 1. Okay? Okay, so what I will try to do next time is just to analyze the full LSB equations close to this transition, and I will show you that there is a set of scaling exponents appearing. And then I will stop with replicas, and I will try to do the computation using the cavity method. And this is the program for the last lectures. Okay?